Hello, my name is Albert and I'll be talking about the intrinsic cost of causal consistency, joint work with Pedro Foto, João Leitão and Preguiça of Novalinks. Causal consistency has become popular as a consistency model, and existing implementations often use some form of metadata to track dependencies among operations. Now this leads to the impression that causal consistency itself is non-scalable and has an intrinsic cost. In this work we show that causality does not have any intrinsic additional cost by itself, when a system already aims to provide reliability. Causal consistency is a consistency model where the happens before relationships among operations are respected. And for such a happens before relation to exist among a pair of operations, for example here operation 2 depends on operation 1, it means that when the replica created operation 2 had already observed operation 1, leading to the fact that operation 1 is a predecessor of operation 2. When such a dependency exists, for example operation 2 depends on operation 1, this means that the system must ensure that every replica executes first operation 1 and only then operation 2. It can never deliver operation 2 before having delivered operation 1. So I've discussed briefly causal consistency itself. Now I'm going to show you some algorithms which can be used to implement causal consistency and their associated costs. Only then I'll go into an approach which shows that we can implement causal consistency without paying any additional cost over already providing reliability. One simple way to implement causal consistency is to use a central node to propagate operations among replicas. The central node would have an outgoing queue for every single replica, and when it receives an operation or creates locally a new operation, it appends it to the outgoing queues for every single replica. This means that we don't need any additional metadata to implement causal consistency, but it does come with a drawback in terms of scalability and availability due to using this single central node. The previous algorithm can be implemented not as a central node, but as using different types of overlay networks, for example a tree. Each node executes the same algorithm as before, and still we don't need any additional metadata for causal consistency. But still the network is fixed, so this does have a great impact in terms of availability when nodes are unreachable. Now there exist many algorithms that do not require such a fixed networking model to be able to implement causal consistency. For example, we can tag operations with a timestamp using Lamport clocks and use a stability mechanism to execute operations. We'll sort operations on the associated timestamps and we execute operations that are marked as stable. Now the stability mechanism itself needs some form of information propagated among replicas, which typically leads to all replicas needing to store some information on every other replica. An alternative approach is to add some metadata to the operations, for example a version vector, which encodes the causal dependencies that it has. We could execute an operation as soon as the version vector that it has associated has all its dependencies met in the local store. Now this does come with a cost in terms of metadata. An alternative to tagging operations with version vectors is to tag them only with their direct dependencies. This effectively compresses their causal histories. For example here, the fourth operation of node number 1 would depend on the first 3 operations of itself, and also on the second operation of node 2 and the first operation of node number 3. Now, this can lead to an inefficient synchronization protocol, as when you receive an operation, you possibly recursively have to ask for the dependencies. So the first 2 algorithms that I discussed, using a central node or a dissemination tree to propagate operations, have actually as drawback that they have a fixed network. It's not really dynamic in terms of adding new peer-to-peers or new connections. When we add this ability to add new connections or nodes, we have as impact that you need some stability mechanism, which requires information in terms of every node knowing information about every other node, or we need to track dependencies, which also has a metadata overhead. Now it seems that as we try to use a peer-to-peer communication model, it's this that leads to us requiring additional metadata. I've shown algorithms to implement causal consistency and their associated costs, And now I'm going to show an approach which shows that we can implement causal consistency without paying any overhead compared to already implementing reliability. So our approach will have replicas storing an ordered list of operations, where each operation only has an associated unique ID in form of replica ID and an operation number. And the interesting part is that this list itself will be ordered in causal order. For a pair of replicas to synchronize, they only need to ensure that operations they receive are added to their own list in a causally respected order. And to do this, we propagate the full list as a first step. And when we receive the list, we add all operations in the same order to the end of our own list. The only thing we have to do is ensure that we don't add any duplicates. One example is here. We have the causal graph on the left, operations A, B, and E, which were created at a single replica, and operations C and D, which were created at another replica. There's a causal dependency between B from B to D, meaning that there was a synchronization step before D was created. Now this means that in one replica it'll have operations A, B, E executed, and in the other replica it'll have C executed, then A and B, which have been received in causal order, and operation D, which was the last one created. At any replica, you can receive the operations from the first replica, A, B, E, and then the operations from the second replica, C, A, B, D, and you ignore A and B because you already have received those. Alternatively, you first receive the operations from the second replica, C, A, B, D, and then you receive A, B, E, and remove A and B because it would be duplicate. Now this works because for the happens before relationship to exist among two operations, the first operation must already have been executed in a replica, which means it already exists in the lists, and then the second operation, the depending operation, is created, which means it will be added after the previous operation in the list, which means they will be stored in the list always in the correct order. Now there are many ways to optimize the previous algorithm by using, for example, acknowledgements to limit the amount of operations that we have to attach to every message. Or when synchronizing with a new connection, we can first send a version vector to limit the amount of operations that we have to send. Interesting here is that if we try to implement reliability, we need to use similar techniques. So there's no really any additional cost that we're paying here. This algorithm does have a nice set of properties. Any pair of replicas can synchronize, so we're not limited in terms of which connections we can establish between replicas. And there's no need to keep information about every single replica in the system, nor is there a need to execute a stability mechanism. This means that we can add additional nodes and new connection among nodes without executing some form of coordination. A fixed number of steps is required for synchronization by, for example, doing it in one step by sending the whole list, or by doing it in two steps by sending a version vector and receiving back only the operations that we actually are missing. The most important part here is that there's no additional metadata required over already providing reliability. The impact of not using metadata to track causality is that we lose the ability to characterize causal relationships among operations. For example, given two operations, operation 1 and operation 2, present in a list, we are unable to know if operation 2 depends on operation 1 or if they were created concurrently. Nevertheless, this is not required to implement causal consistency itself. So I went over common solutions for implementing causal consistency, and we went over the costly stability and synchronization mechanisms these typically have, and discussed metadata overheads. These aspects are each made worse when we dynamically add or try to remove nodes from the system itself. We showed an approach where, using simple ordering techniques, we can implement causal consistency without any metadata costs additional to already trying to provide reliability. We do lose the ability to characterize causal dependencies, but these are often not required by the application, we just need the system to provide causal consistency. And to conclude, for a system which aims to provide reliability, the intrinsic cost of providing causality is zero. And we believe that this motivates causal consistency as a practical and adequate consistency model. Thank you.